Hi students. So in this video we'll see how to plot the root locus when the open loop poles are in complex position. So now we have a third order system having open loop poles at -1 and there are two more poles having its real part as -2 and its imaginary part as plus or minus j5. So this is that -1, so let us take this as -2. So let us consider this as plus j5 and then maybe somewhere here it is. So let me take this as minus j5. So this is the real axis. So we need to find, first we need to identify which part of the root locus is a part of, which part of the real axis is a part of root locus. Okay, looking at this, here this is a part of root locus. It leaves -1 and goes towards infinity because there is an asymptote lying at 180 degree. You can actually find out what are the asymptotes. Asymptote centroid is, so let me find out. Centroid of asymptotes is nothing but real part of poles. So we have the real part of this pole as -1 and the real part of this pole is -2. Of this one is again -2, and we don't have any more zeros, and it is p minus z. P minus z is 3. It's actually -5/3. So -5/3 is the pole position. So we have, so it is 5 which happens to be 1.66. So it is -1.66. So that is the pole position, maybe somewhere here. So this is the centroid, and we know the angles are 60 degree. Let me write a very light lines, so maybe with the yellow color. So this is 60 degree, this is 180 degree, this is 300 degree. So these are my asymptotes. Let us find the angle of departure for this. Because we have a complex pole, we need to find the angle of departure. Okay, angle of departure is given by theta d is equal to 180 degree plus phi, where phi is summation of theta z minus summation of theta p. So we don't have any zeros here. So actually summation of theta z is 0, whereas summation of theta p we have actually 2 poles. So that's why it is, since I'm interested in finding the angle of departure of this, so let me join this to this and then this to this to find the angle. So if I treat this as theta p1, then this is theta p2. So I can find theta p1 is straight away, theta p1 is 90 degree, whereas theta p2 is actually 180 degree minus tan inverse of opposite is 5 by this is 1. So it is minus of tan inverse of 5. So this happens to be the value. So let me get the calculator. Give me a minute. Okay, now I'm with the calci now. So let us find this angle. So it is now 180 minus tan inverse of 5, which has to be which will be 101 degree approximately. So summation of theta p will be 191 degree. So So if you just sum it up, so what is theta d then? So it is 180 degree plus of 0 minus of 191 degree. So this happens to be minus 11 degrees. So angle of departure is minus 11 degree. So which you can treat, okay, suppose if you treat this as 0 degree, so 11 degrees comes somewhere here. So this is, of course, minus 11 degree is there in the clockwise direction. So you can treat this as minus 11 degree. So corresponding to this one, this will be at plus 11 degrees. So plus 11 degree is the angle of departure of this. So we know at what angle it departs. Next, what we have to find is, we need to find out what is the point of intersection of this root loci with the imaginary axis. So for that I should know the characteristic equation. So let me find the characteristic equation for this. So if I write it here, del of s happens to be, so now it is s plus 1, this happens to be s square plus 4s plus, it is 2 square plus 25 square, which is nothing but 2 square plus 5 square is 25, that is 29 plus k equal to 0 is my characteristic equation. So this further reduces to s cube plus 4s square plus 29s plus s square plus 4s plus 29 plus k. So it is now s cube plus 5s square plus 29s plus 29, sorry, this is not 29, 33s plus 29 plus k equal to 0 is my characteristic equation. So let me write the roots array and try to find out what is, let me rewrite that equation. So it is now, let's write it here. So it is s cube plus 5s square plus 33s plus 29 plus k. 29 plus k equal to 0 is my characteristic equation. Let us verify it once. So it is s cube, okay, 4, 29, this is so fine. Cube, this is 5, this is 33, this is 29 plus k, fine. So now let us write the roots array for this. Write the roots array to find the point of intersection of root locus with the imaginary axis. So it will be 1, 33, next it is 5, 29 plus k, then s power 1 will be 5 into 33 minus 29 plus k divided by 5, 0, and then 0 is 29 plus k. So this term can become 0 when 5 into 33 minus 29 plus k is equal to 0. Therefore, of course, then this will be k margin. So what is k margin then? K margin is 5 into 33 minus of 29. So if I do this, 5 into 33 minus 29, that will be 136. So k margin is 136. So considering this k margin, if this k is 136, then this becomes 0, then you end up with the auxiliary equation, which is nothing but 5s square plus 29 plus k margin equal to 0. So this becomes 5s square plus, so it is 29 plus, of course, 29 plus 136, which happens to be 165, equal to 0. then a square is equal to minus of 165 by 5 by 5, 165 by 5 is 33, because minus 33, then the roots are plus or minus j root 33, that is root of answer is 5.74. 5.74 is the point of intersection at it will want to cross the imaginary axis. So coming back to this, so point of intersection is plus or minus j 5.74, meaning it leaves at an angle of minus. So let us identify where is that 5.74. If you approximately write it as plus j 5.74, this will be minus j 5.74. It actually leaves, so let me write it using this. So it leaves at an angle of minus 11 degree and then goes in this direction. Then finally it goes in parallel with the asymptote. It goes like this and then comes here, goes like this. Oh, this is my root locus, so it is moving like this. So system is stable as long as the value of k is less than 136. So system is conditionally stable. That is, if the value of k is less than 136, then only system is stable. Of course, anything between 0 and 136. If k is more than 136, then system is unstable. If k is 136, then it oscillates at a frequency of 5.74 radian per second. So let us see the MATLAB implementation of the same. I think it is the same. Do we have that? Let me just, this is not, this should be changed to, that is now 4, this is 4 and 29. This is 29. So I have, this is s plus 1 over s plus 1, then it is 1 over s square plus 4s plus 29. That's what is s square plus 4s plus 29. So this is, it is this one. So we are talking about this s square plus 4s plus 21, and this is the other one. So if I go back here and then run, so what is the transfer function you have? It hasn't run yet. Let me run this again. Okay, this is the transfer function. You can see now this is living at an angle of, let me just try to zoom it. Let me try this again. See now, this is living almost at an angle of minus 11 degrees. Let us try to find out if this, okay, I can get the data point. So this is the data point what we are looking at. So this, can you see it is 130. So we want to have, now 136, it is still to the left side, so that is 132. Maybe when you go very close to that imaginary axis, okay, let me just zoom it further. Now let me just zoom this. Now if I go here and then place my data point, okay, now let me place it here. No, data point I cannot place it there, it's there to the left. Can I place the data point here? No. So this is 132, poles are there here, and of course it is a point which is there to the right. You can see the pole position is positive. the real part is positive. So let me go back to this. Okay, run it again. Let me run this. And this is how you can able to verify the problem that we have solved on paper using the MATLAB code. So let us move on to one more. Let me just take this. So let us consider complex pole and complex zero and try to see how do we find angle of departure as well as angle of arrival. So let us take g of s into h of s as k by, so let us take randomly s plus 2 s or minus j3 and take this as s plus 3 plus or minus j2. So we have poles and zeros situated at, so this is mine. If it is minus 2, if it is minus 3, then the 0 is at width height, because this is at plus j3, this is there at minus j3, this is minus j3, and of course my poles are somewhere here. So this is at plus j2, is at minus j2. Now we know that since there is nothing on the real axis, so now there is no question of root locus on the real axis. Now let us find what is angle of departure. Angle of departure for this, so which is at minus 2 plus minus 3 plus j2. This is minus 3 plus j2. So for that, so let me join all poles and zeros to this one. So this angle is, this is one, this is the other one, and this is the third one. I am just approximately writing. So this is one angle, theta z1, this is theta z2, this is theta p. So we have two zero angles and one pole angle. So what is this? This is actually 180 plus phi, which is nothing but 180 degree plus summation theta z minus summation theta p, which is nothing but 180 degree. So what is summation theta z? We actually have 2 z, okay, 2 theta z, that is theta z1 plus theta z2. So let us try to find out what is theta z1, which is nothing but, okay, one is this plus this angle. So shall I write it as 180 degree plus how much is this height? This height is, of course you can write it as tan inverse of this height is 1 and this distance is also 1. So it's actually 45 degree, that is tan inverse of, we know that tan inverse of 1 is 45 degree, 45 plus 180 is 225 degree is this angle. This is 225 degree. How about theta z2? Theta z2 is, it is, this is actually 90 degree plus this value. So it is 90 degree plus tan inverse of this is 180 degree, that is whole angle, 180 degree minus this, 180 degree minus how much is tan inverse of opposite is, from 3 to 2 it is 5, so it is tan inverse of 5 by, so this distance is actually 1, because it is 3, this is 2, this is tan inverse of 5 by 1, tan inverse of 5 by 1. So then what is this angle? So tan inverse of 5 is, okay, it is 180 minus tan inverse of 5. As we found in the previous example, this is 101 degree. So you need to sum it up these two. So it is 101 plus 225. This happens to be overall summation of theta z is 326 degree. But you can see theta p1 is actually 90 degree. So summation theta p is 90 degree. So I need to substitute this as, so this is 326 degree minus 90 degree. So 326 minus 90 plus 180. This is actually 416 degree, which happens to be minus 360 is 56 degree. So it is 56 degree. So angle of departure theta d happens to be 56 degree. For this one, for this it will be minus 56 degree. So what we'll do is we just write an approximate line at 56 degree. So this is 0 degree, this is 90 degree. Shall we take this as somewhere here? This is 56 degree. This is plus 56 degree. So here this will be minus, approximately minus 56 degree. So this is 56 degree. This is minus 56 degree. So this is angle of departure. We need to find the angle of arrival. So for finding angle of arrival, it is 180 minus 5. So it is theta A is nothing but 180 degree minus 5, where 5 is again summation theta z minus summation theta p. Now we need to consider, we need to join this line. So this to this, this to this, and this to this. So they are actually theta. This is, so let me write it as theta z1. This is theta p1. This is theta p2. So now this theta p1, theta p2 are different. Now this is different. So what is theta z1? So theta z1 is, so summation theta z, you have only 1 0 angle, which is nothing but 90 degree. How about theta p? Theta p has got theta p1 plus theta p2. So if you find theta p1, which we have taken this as, this is theta p1. So what is this distance here? So this height is from 2 to 5. So it is tan inverse of 5, and this is hardly 1. So tan inverse of, so this is tan inverse of 5 by 1. Correct? This is, of course, this is actually this much only. So tan inverse of 5 by 1. And how about theta p2? Is it not tan inverse of 1 by 1? So theta p2 is actually tan inverse of 1 by 1. So 5 by 1 happens to be tan inverse of 5 is 78 degree, whereas this is 45 degree. So coming to theta p, so summation theta p, it is 78 plus 45, which is 123 degree. So now we have phi is equal to summation theta z minus summation theta p. So theta z happens to be 90 degree, whereas theta p happens to be 123 degrees. So this is minus 33 degrees phi. So what is then theta a? It is 180 degree minus of minus 33, which happens to be plus 180, 213 degree. This is the angle of arrival. So now what we have to do is, so let us find 213 degree. So 230 degree is the angle of arrival of this. Angle of arrival of the root locus to this 0. So this is angle 0, this is 180, and you can just think of, let me just rewrite that boldly here. Let me just take out all other things and then write only this. So this is minus 2, this is minus 3, and we have this at plus j3, and this is at minus j3, and we have this at plus j2, and I have this at minus j2. And we know that angle of departure is where is that angle of departure? 56 degree. So we draw a line at an angle of 56 degree. This is 56 degree line, and this is minus 56 degree line. And what is angle of arrival? Angle of arrival is 213 degree. Angle of arrival is 213 degree. So 213 degree comes somewhere here. This is 0, this is 180. 213 is from here another 23 degree. So this is somewhere here. So now this corresponds to 213 degree. For this 0, it happens to be minus 213 degree. So minus 213 comes somewhere here. So this is minus 213 degree. So the pole leaves here, and then it just enters. So maybe it's just going like this. So this is how it is going. See now, this is how it is going. So this leaves at an angle of, this pole leaves at an angle of plus 56 degree and enters the 0 at an angle of 213 degree, whereas this leaves at an angle of minus 56 degree. This is minus 56 degree, and it arrives at an angle of minus 213 degree. So now system is absolutely stable, because the value of k is 0 here, the value of k is infinity here. For any values k between 0 to infinity, the poles are always onto the left hand side of the S-plane. So this is how it looks. So let us see the MATLAB code of the same. So I'll just copy paste this and then slightly alter here itself. Okay, now this is fine. I'll make this also at, so this is now s square plus 4s plus this is actually 4 plus 9 is 13. And the second one is s square plus 6s plus this will be 9 plus, okay, that will be same 13. So that will be again 13. So let me plot how it comes. Let me see how it comes. So it has to come this way. So it has to come this way. Let us see what we are getting. This is my transfer function. Okay, this is not relevant now. Let me just take out that. If I run, okay, let me just first save this. No, it's not yet saved. Let me save. Okay, let me now run. See now, this is living at an angle of 56 degree, and this is arriving at an angle of 213 degree. So this is what we have in our plot also. This is what we got it. See here? This is not the same plot what we have. So this is how it is going. So this is living at an angle of 56 degree and arriving at 230. So when I say arriving, so this is arriving like this. So it is at an angle of 213 degree. So when I say living, so this is the angle at which it is living. So this is, you write a arc for 216 degree, you just draw a line for 213 degree, just draw a smooth lines joining that. So that's what we have over here. So this is how it is living, this is how it is ending. So same thing is true for this. Hope you got this one. So we'll see a few more problems in the next video.